This is an AQA A-level chemistry topic from year 13. We're looking at acids, bases and buffers. This is part 4 of this topic. We've looked at lots of calculations, and in this one we're going to focus on pH curves. So as always, I'm going to recommend you pause it, have a go, and then see where you are understanding and what might need a little bit more time and effort to be spent on it. So as I've said, we're looking at acid-base titrations, looking at pH curves, and we're also going to look at the term equivalence point, see what that means and how we can use it. So in the first instance, we're going to take a look at a pH curve here. And question at the bottom, suggest an acid and an alkali that might have been used that would give us this curve. First thing that I'm going to look at is we've got a very low pH we're starting with, so that makes me think it's a strong acid. Similarly, we're going to a very high pH at the end, so that tells me we think it's going to be a strong base or alkali. Now a strong acid, it's monoprotic because you actually get 2 steps in a diprotic pH curve, so you could go for HNO3, I've gone for HCl here. And a strong base, I'm going to go to my default on this, I would always just go for NaOH as a very clear answer. There is also another clue that we're dealing with strong acids and bases, and that's that these stay very horizontal for a long time, and then we get this sudden change. You're going to see a difference on some further examples that will help you to differentiate. Do the same for this one. What type of acid, what type of base might we be using? Well, we are starting with a weak base. The pH is still relatively high, but we are seeing a different shape here. It's not going across horizontally and dropping. We get this little lip. There's a rapid fall, then it levels off before the big change where we neutralize. So that's a giveaway that we're dealing with a weak base, and the reverse is true when we look at a weak acid as well. But this is definitely a strong base because we have got this very, very strong dip, but then we carry on down and we level off. We've not got this lip at the end. A weak base, we might think of NH3. A strong acid, again, I've gone for HCl. And we've got another example here. What might this be? Well, we're seeing that we're starting with a slightly lower pH and ending with a higher pH. So that immediately makes us think weak acid, weak base. We've also got the lip, and we're seeing this, it is leveling off here, but we're not seeing it go down anywhere near as far. So a weak acid, we might be going for ethanoic acid. That's ethanoic acid bringing us down below 7, but not going very low at all. Ethanoic acid, commonly known as vinegar. And ammonia as our base to begin, dipping down. The other dead giveaway here that we're dealing with weak is we've not really got a rapid change at the equivalence point, and that has an important impact when we actually start to look at indicators as well. So just to summarise, have a think about this table, see what you can fill in, see if you're confident that you would fill it in. So we want to know for a strong acid, strong base, what would my 2 components be? And I would combine peak 1 and peak 4, where we've got this very rapid change. We're going fairly horizontal before the change and staying fairly horizontal after. And when we're looking at where the endpoint would be, well, we're looking at this very steep part of the line, and exactly halfway up for our 1 and 4 is I2. So we would expect that to be our endpoint, the point at which neutralization is reached. So let's move on to a strong acid and a weak base. Well, my strong acid is still 1, but my weak base is coming up. It's stopping lower down, as we'd expect at a lower pH, and we've got that little lip there as a giveaway. And when I combine those two, my endpoint is going to be I1. I've got a rapid change there before it levels off, moving into part 3 of the curve. A weak acid and a strong base. Well, a weak acid, I'm going to start at number 2. I've got my lip, I'm at a higher pH, but my strong base means I'm going to go right the way up and along here. And for this one, my endpoint would be at I3 on that steep part of the curve. Really important for when we get to indicators later. The weak acid and the weak base is going to be 2 and 3, and there isn't really a measurable endpoint here where a pH would rapidly change in colour, and that's why that box is blacked out. So there's a question here that I've already spoken about, but you can think about how you might word it, how you might explain it. And we are seeing that with a weak acid, weak base, there really is no rapid change in pH when I add a small volume of acid and alkali. You will know, and you'll see from the graphs, and you'll know from the practicals you've carried out, that it can be a single drop that can take you from a very low pH to actually going beyond a pH of 7 to a very high pH. We don't get that rapid change with a weak acid, weak base, so we don't get a rapid colour change with an indicator. So the equivalence point is the point when just enough base has been added to neutralise the acid. When the equivalence point is reached, there's a major change. And again, I'm just going to reiterate, that's really important, as you'll see in the next video, for where you are going to choose the appropriate indicator for the reaction that we're doing. But I'm going to finish off with something that you're very familiar with. We can calculate the concentration using the equivalence point. And you've done this before. This is a straightforward titration calculation. So if you want to remind yourself of it by looking through this table, pausing, and then there's a couple of examples for you to try. So have a go at these, and then when you're ready, we can review. So I'm going to start by drawing my table, C, V, N and ratio. I've got my HCl and KOH. I'm going to take the data that's provided by the question. You can see from the colours where I've taken those from, and you can see that I've converted my volumes to decimeter cubed. Because concentration is in moles per decimeter cubed, volume must be in decimeter cubed. I'm also going to put the equation up. This is a 1-to-1 ratio of HCl and KOH. Now, because I've got a C and a V for KOH, I can work out the number of moles, 1.25 by 10 to the minus 3. And because it's a 1-to-1 ratio, I know that means I've got 1.25 by 10 to the minus 3 moles of HCl as well. Now that I've got an N and a V, I can work out my concentration of HCl. And it comes out as 0.0625 mol dm to the minus 3. On to the next one. Table drawn out once again, data submitted and color coded so you can see where they've come from. The equation shows us that NaOH and HNO3, and it's a diprotic acid and it's a monoprotic acid and a monobasic base, that it's a 1-to-1 ratio. I can work out my number of moles for NaOH. I can use my mole ratio to see how many moles of HNO3 I started with, or I reacted. So then I do my N over V calculation. I get my concentration here is 1.25 moles per decimeter cubed. So that takes us to the end of this video. Thank you for listening, and goodbye.